Okay, we're going to look at patterns in nonlinear functions today. Last time we looked at linear functions. A nonlinear function is a function whose graph is not a line. So all the ones we looked at last time were lines when we plotted the points. So here's some examples of linear functions. Notice the one in the middle is what we call a discrete function. That's what we graphed last time. We had several graphs that if we connected the dots, it would make a line, but it didn't necessarily make sense to connect the dots. And these are examples of nonlinear functions, all of which you study as you move on in algebra, move to algebra 2 and pre-calculus. The first one is a parabola, the second one's a cubic, an x cubed type of graph, and the other one's an absolute value graph. That's the third one on the right. It's an absolute value of x. So linear functions make a line, nonlinear functions do not. We're going to look at nonlinear functions today. So let's look at our first nonlinear function here. It says the area A in square inches of a pizza is a function of its radius, r, in inches. The cost, c, in dollars of the sauce for a pizza is a function of the weight, w, in ounces of sauce used. Graph these functions shown by the tables below. Is each linear or nonlinear? So one of these I think is linear and one is not. So let's do our best to graph these. We got values like 12.57 here. And we'll do our best to graph that on here, estimate where that is. But with a radius of 2, we're at 12.57, so that may maybe right down here. We'll make a big dot. 4, we're at about just a little over 50. So at 4, we're just a little over 50. At 6, we're at 113. At 8, we're at 201. And at 10, we're at 314. So there's one graph. Almost looks linear. You can see that it's actually not. If you draw a line through these or curve through these, you'll see that it curves up in what's called a exponential graph. So it's kind of growing a little more. You can see there's not a common difference between each of these corresponding sets or sequential sets of areas. So it's growing up. It actually is its area, and so we see squared units here, and so it's actually that right-hand side of a what's called a parabola or quadratic equation. So definitely curving, not linear. Look at the next graph over here. We've got, you can see here, it's got a common difference of 80 cents between each one. So we already know from last time that's going to be linear. So if we go over 2 and up to 80, I have a dot about right there. At 4, I'm at $1.60. And then at 6, I'm at $2.40. And at 8, I'm at about $3.20. And then at 10, I'm at $4. So if you draw a line through those, you'll see that it, well, draw a curve through it, it makes a line. And so this one we would call linear. And this one we'll just go with, we won't worry about what type of graph it is. We'll call it nonlinear. Alright, so example of a linear graph and a nonlinear graph. The table shows the total number of blocks in each figure below as a function of the number of blocks on one edge. It says, what is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. So as we look at the table here, we see with one block, we just have we have a cube actually with one block. You can see in the picture over here. And if I move to a 2 by 2 by 2 cube, if you think of three-dimensional, 2 by 2 by 2, it tells us how many blocks we have. This one's 1 by 1 by 1. This one is 1 by 1 by 1, which has a so if there's one block on the edge, total number of blocks would be 1. We call that the volume. The second one, 2 by 2 by 2, would have a volume of 8. The total number of blocks would be 8 blocks that are 1 by 1 by 1 in dimension. And then 3 by 3 by 3 would give me the 27. If I went 4 by 4 by 4, 4 times 4 by times 4 is 64. And so my next coordinate would be 4 comma 64. And then 5 by 5 by 5 would be 125. And so my next coordinate would be 5 comma 125. This is what we call cubing. cubing each time. It actually has the equation, well, let's describe it in words first. It's number of blocks on an edge, so each time we add a block, the total number of blocks is cubed. In other words, we take x and cube it. It's y equals x cubed is our graph. Definitely nonlinear. If we graph it, it looked like this. At 1, we're at 1 here. Way down here at 1. 2, we're up to 8. 3, we're at 27. 4, we're at 64. Looks similar to the one I just did, although it's only half of what's called the cubic function. It's the positive half of it. 5, I'm at 125. So we see this curve. You can see it curves up a little faster than our last one. That's y equals x cubed, and that is an example of a nonlinear function. And it's really just graphing volume of the entire cube based on the number of blocks on an edge. All right, let's get one more example here of a nonlinear function. It says the table shows the number of new branches in each figure of the pattern below. What is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. So let's see if we can figure this out. Looks like we have, with a number of figure, that's a 1 figure, 3 branches. We go to the second figure. Each of those branches splits into 3. So we have 9 new branches. And then the next figure, each of those branches then splits into 3 again. So we have 3, 6, 9, 12, 15, 18, 21, 24, 27, just counting all these guys are on the outside. So it looks like each time we triple. So going this direction at least, we go 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is going to be 81, 81 times 3 is 243. So, we call that just a vertical pattern. We have well, this is a horizontal graph, but a horizontal pattern in this case, I guess. But going from one of these to the next, we're multiplying by 3.
Good morning, Eldorado.
Okay, so let's see if we could describe in words what's happening here. Each time we extend from one figure to the next, the number of branches triples. So and in terms of an equation here, we have what's called an exponential equation, which is new for you guys. You may not recognize it, but it's y equals, it's this common multiple that you see here. It's times 3 each time, you'll see, as we go from one to the next. That becomes what's called the base of the exponential equation. And the power is the variable, so it's 3 to the x. It's y equals 3 to the x, definitely a nonlinear graph. And when I graph it, it goes like this. It grows pretty quickly. So 1, I'm down at 3. 2, I'm up to 9. 3, I'm at 27. And 4, it's at 81. Now it's going to really start to take off. And at 5, it jumps all the way up to 243. It's a little steeper than the last one I did. It's exponential growth. It grows even faster than that cubic in the previous one. So that's it. There's some examples of some nonlinear functions. Just means they don't make a line. So we saw today just a couple of them. We saw this one right here, which was actually what's called a quadratic function. It's an x squared sort of function. We saw this one right here, which was a x cubed function, grows a little faster than x squared. And then we saw final one was what's called an exponential function. So the exponential function grows even faster than the previous two we saw. So there's some examples of some basic nonlinear functions that we're going to be studying.
Hi.